Good evening and welcome to the next edition of Let's Talk AI. Today we're going to look at devices on the edge. So we have with us Dr. Aftab Hussain from our Center for Wireless and Embedded Systems.
Hello.
Aftab, welcome.
Thank you. Nice to be here.
Yeah, so let's get started, Aftab. So what is this whole thing about edge? What is edge? Let's just start with setting some terms out of the way.
Yeah, I think what we have to realize is that edge computing is not new. We have always been doing edge computing. It's just that
the buzzword is new, but
the buzzword is new. But what used to happen is like when if you had a PC in 80s or 70s or 90s or whatever, you were basically doing edge computing. It's basically doing all of your information processing at a terminal, at the local terminal
before
that is
available.
available.
Something to the backend.
Before
somewhere.
it sent something, because there was basically no backend, there was emails and some networking. That was the only backend you had. So there was no computing at the backend. Everything was happening on your personal computer, and that was it. Then came cloud computing, and that was the big buzzword 10 years ago or 15 years ago, right? And because of that, what happened is people realized that you can actually do a lot of computing away from your computer. All you need your computer is for either to display that information as a monitor or to capture that information as some kind of a sensor or some sensory input that you would need locally. You would just capture that information, send it somewhere, and that is where all the processing will happen, right? So that became the buzzword back then, like cloud computing was the thing. But because of that now, because that has caught on and everybody is doing some part of it, this edge computing has returned basically. So we are basically gone from edge computing to cloud computing and back to edge computing, which again means that instead of sending all the information that you're capturing on locally to the cloud for processing, you will basically do some processing on it wherever you're capturing itself, like on what we call the edge itself.
Before you send it.
Before you send whatever information you need to send. So that is basically edge computing. And it's nothing new.
And then at some level, there's a hardware angle to it, right? We're not talking about PCs or, yes, technically that's also edge.
Right.
But when we look at edge computing now, we are looking at like sensors where there's some sensor, there's some data being collected and processed before, right? Is that common?
So that is the common understanding. The interesting thing is hardware developers don't differentiate between the two. For me, at the end of the day, everything is a microprocessor.
A PC or a mobile or
everything is a microprocessor.
Sensor, everything is the same.
Some processors are better, some are more powerful or faster, and some are not. That's how people differentiate between a PC and a mobile and some other hardware. So at the end of the day, your all of those devices.
The only difference is either there's a human being next to it or not. Other than that, the computing is the same.
Even in PC and mobile, there is a human being next to it. Even in some sensors, there might be. So at the end of the day, it's a very blurry word for a hardware engineer to figure out what you want to call an edge computing. So I basically call everything that's
not centrally run. Anything running on the outer edges is
where either data is being captured or data is being displayed.
So it's becoming now, I mean, the whole term is becoming more kind of relevant in the IoT world.
Yeah, absolutely.
So how does it fit into the whole IoT world?
So let's start by knowing what IoT is.
Okay, let's get that out of the way first. Yes, what is IoT? Let's agree upon.
The problem with IoT is that if you ask 10 different people, it's 10 different definitions of IoT, right?
Absolutely. Yeah.
So I think, so one of those 10 definitions, I keep going to like all of these literature and see what people are defining IoT as. One of the definitions I liked is that IoT devices make inanimate things animate. Okay, so you can now with the help of IoT suddenly talk to your table, right, or your chair or your door. Like what they have to say or what information they'll provide is different for different objects, but they're suddenly talking to you, right? For instance, like people are developing smart chair, which will tell you whether your posture is right, whether you're drowsy, whether you should basically take a walk because you have been doing your.
That's a very interesting way of looking at it.
Too much. So your chair will suddenly talk to you, like, hey, why don't you take a walk? It'll be good for your health. So anything that makes inanimate objects, animate is what I call IoT. But more formal definition is that it's a network of things. Like things are there, again, the same chair, table, your street lamp, and all of those things, they are normal things. If you network them, if you basically make a network out of them so that they can communicate with each other and with, say, a central server or a cloud, then we call it an IoT.
And then like now we are saying like it's not just a sensor. One way of looking at it is like there's a sensor on the street light, and that continuously sends data to some server where there's some piece of software running that's processing the sensor, maybe to turn the light on.
Right.
Now, when we try to put that's a dumb sensor. Now we're saying like we'll have smart sensors which doesn't send always, but only sends when some significant change happens. Right? So that's where edge comes in. It's a very trivial edge, but you can build on that, right?
Yeah, so that is the difference between edge computing and cloud computing, and I think you nailed it well. The major difference is how much data you are basically transmitting. Right? At the end of the day, what happens is, like, you imagine, like, right now, we have all our phones are there, right? I mean, we have the network operators, Jio, Airtel, and all of those network operators are there. You will face some congestion or the other at some point of time when it's busy or something, like when some festivities are going on, when New Year's Eve is there, everybody's trying to call each other. There is a lot of network congestion that happens. Imagine this is only with something like 1 billion mobile phones, right, in India, or less than that, somewhere that range. What people are saying about IoT is that in the next 10 or 20 years, we'll have 50 billion devices all over the world, which is basically like 8 times more than the human population. So if you project that to India, it's basically 10 billion devices. So instead of now 1 billion people calling each other, there'll be 10 billion things.
Devices on some network.
On some network, either trying to call each other, communicate with each other, do something or the other, right? And you might say that the sensor data are generally trivial, like voice information is very heavy and sensor data can be very, 1 or 2 bytes or few bytes. But I would argue that some sensors are actually very heavy data as well.
So like in this city, we have just the city police network has 1,000 cameras.
Exactly.
I mean, 10,000 cameras.
Yeah, I was actually coming to the exact same example.
There are 100,000 cameras, as per the trade establishments, which could be connected to this network.
Yes.
They're legally bound to give the feed.
So you can imagine that if you start connecting all of these, say 10,000 cameras, 1 million cameras,
and many of them are HD cameras.
HD cameras, they are basically giving you throughputs of megabytes per second. And then all of them get connected together, multiply that with 1 million, you're basically in terabytes per second already, right? And then if you take it to the city level or the country level, the amount of data that will basically be, the throughput that will be there will be humongous, just with these billions of devices that are going to be connected.
And that brings the whole that whole big data angle into the picture now.
It does, but we'll put a pin on that. But what I was trying to say is, because of this, the biggest problem, the headache that you will have is how do you transport data, right? You want everything to be done centrally. That's a good thing because it saves on, processing everywhere, like locally. But the problem is you have to then transmit all of that data first to the cloud, do processing there, and then transmit everything back or some part of it, whatever actuation back, all the way to whatever needs to be done, right? For instance, in a display or something. So all of that actually, just the sheer scale of devices that are going to be there on the network actually makes this a very, very big logistical problem, just to how to transmit data from one place to another, from edge to cloud. So what we do is, that's why edge computing is now becoming a buzzword, is what people realize is, okay, let's not transmit everything, right? For instance, the example that you give, video feed, or a similar example is if you want to say, take a picture and figure out how many people are there in a crowd, right? There are two things you can do. You can either send the entire picture to the cloud, do some AI on it and figure out like head count, how many people are there. Or you can take the picture, do the processing there itself, like where the sensor is, where the picture has been taken, and just send the head count. The difference between these two in terms of data transmission is huge.
Few bytes versus
megabytes of data. So you're basically saving millions of times worth of data and again, if you have multiple cameras, if you scale up anything that is doing these kinds of things, you tend to see a lot of savings in data transmission, data storage at the cloud, and all of those things become easier. So that's why this edge computing for IoT is becoming a big.
Even the smaller sensors also, like, I mean, with the very fine granularity of sensing possible, even if you're looking at like maybe like its temperature in a location, you could possibly send it like every millisecond or every microsecond.
Right.
And often we don't think that you don't need it. If it's, especially we're talking about comfort climate control.
Right.
You probably don't even need every second.
Yeah.
Data is available, doesn't mean you should take it.
Right. Correct.
And I think some of the data explosion is probably happening because of things like this, where even though you don't need, just because it's available, you're getting it.
Yeah, no, that is definitely a problem as well. Like when we design very, very scalable solutions for IoT applications, like at a city level, for instance, we have to be cognizant of the fact that how much data we are going to be generating, say, as a throughput, like in megabytes or gigabytes per second, as well as how much data we are going to basically be storing in terms of the actual archive data. Both of those, and particularly, and both of them have their engineering challenges. Like the data throughput has to be low, and the archiving also has to be as low as possible without giving away any features that you would otherwise want your smart city to have. So, for instance, that climate control thing, you can take temperature data every 10 minutes also, and it's still probably going to be okay.
Exactly. It's a comfort. So, it's not going to change so much in 10 minutes.
Yeah, exactly. So if you're sending 10 minutes per every 10 minutes, it's only 2 or 3 bytes of data, then you're basically good, because you have to realize that it's not just 2 bytes per 10 minutes. It's 2 bytes per 10 minutes into 10,000 different sensors.
Yes.
Right. So then it becomes a decent throughput. And then you're okay. I mean, but if you basically look at it from an individual sensor point of view or an individual like a building point of view, then you basically tend to miss out that scaling factor. Like if you scale it up on a city level, what would happen to the data throughput?
And we're talking about sensors, all kinds of stuff now.
Yeah.
Like and this cameras is one thing. There are noise sensors, pollution sensors.
There are dustbins now. I mean,
yes, and yes.
So,
exactly. So, and there could be any number of them. Those could run into hundreds of thousands exactly. In a city. And so, what are the how do these converge? Right? At some level, there is there's IoT, there's big data, there's edge. Now, what is the convergence amongst this?
So I think at the end of the day, what we'll have to figure out is how do we optimize things, right? I mean, it's not that just because the data throughput has to be very low, let's do everything on the edge. That doesn't work. That has its own problems. Let's do everything on the cloud, has its own problems, like the data throughput one. So you have to basically now figure out.
Very pragmatic and smart.
We have to have a pragmatic approach of what to do on the edge, what to do on the cloud. For instance, the same example that I was giving, that if you want to figure out in a photo how many people are there. If it's a stationary photo, it's good. I mean, you can take that photo, do some processing on the edge itself. You might find a processor that able to handle some amount of intelligent algorithms that will determine those number of people in a photo and send that information. So that is great. But if you do it real time, like for instance, you have a data feed or a video feed of 30 frames per second, right? So you have to basically do it in 1 by 30 seconds. Every frame you have to basically process and send the data of how many people are there in that frame. So as a part of, say, crowd control for large gatherings. So that will become tricky. Then your edge is actually now becoming very, very powerful, or you have to basically put a very powerful processor on the edge, which means again it has to be supplied that much power. The expense of it increases. The cost increases, and then things like if you have a very powerful processor, how the heat management is there? Like you have to have a heat sink and fans and everything else. So it starts looking like, instead of a sensor, it starts looking like a GPU.
One small part of your cloud there now.
Exactly. So instead of having everything on a data center, you basically put everything on the edge. But they are still the same. At the end of the day, somebody has to do that processing. So we have to be smart about where to put what.
And also, like, the use case is determined. Like supposing you just refer to crowd control. Crowd control in an area involves multiple cameras. So one camera cannot do the job because you're going to have a whole area that is being mapped.
Right.
So that's again a trade-off in terms of what you can do on the edge and what you cannot. Some of these algorithms you can't run on the edge when it involves multiple cameras.
Yeah, exactly. So if you make a network that requires multiple sensors to talk to each other, at the end of the day, you have to basically have a central server.
Yes.
Running a particular algorithm there itself and running some algorithm on the edge itself. So both have to basically work very well in tandem.
So at some level, we should view this as edge is an extended arm of the central. There's one logical large application being run, and edge is an extension of that central facility where somebody decides centrally that, okay, I can run this part on the edge.
Yeah, exactly.
So the context is still one some central application. In this case, if it is the crowd application with the crowd monitoring, the context is the central application that's monitoring crowd in an area.
Right.
It can choose to delegate some processing to the individual cameras.
Right.
And the rest it would do itself.
That, or what you can do is, for instance, if you want to make, for instance, have some uniformity, because what will happen is if you start delegating what part of algorithm will be run on what sensors, you have to make individual sensors case by case basis. But that I don't think you would be able to do. You'll have to manufacture all the cameras together, probably with the same processing capability, and you want to, once you have done it, you want to use that processing capability instead of it lying around.
Yes.
So what you would end up doing in some situation like this is that you will basically do edge computing with to figure out, say, number of people or where they're going and everything. That only that information is sent to the cloud. Then the cloud runs its own algorithm to determine whether there is a possibility of stampede, because that's again a processing. But that processing cannot be done on the edge because individual cameras don't know where the entire crowd is moving, like you just said. So that information is only there at the cloud. So large scale or deeper intelligence of, for instance, okay, should we have some crowd control, or should we have more people telling the crowd to go this way or that way? Some stampede possibilities are there, or some other events that can occur. That only the cloud will be able to figure out based on the input that it gets from the individual sensors.
So there was this use case there was there in one of the stadiums where you can summon a drone to come and take a picture of you when you're watching the football game in Europe, in Amsterdam.
Right. Okay.
So, I mean, it is interesting. So it can't be just a drone sent. It has to have, and when you're summoning, you're not summoning the drone. From your app, you're letting some central something running in the cloud know that, and you're not even telling where you are. The app figures out you're at so-and-so seat. And then the drone with the camera is sent, and they will take a picture, and the drone knows who you are, or at least the drone's backend knows who you are, and then the picture comes to you.
Right.
And there's one more app where it puts it on Twitter or Instagram directly.
So everything is done for you. Basically,
it puts it on behalf of the.
The next level of it is you just have to think about it, and everything will be done.
So your drone will put it for you, and somebody else's drone will read it for you. So now if you look at the other aspect of edge is like, it's not that the camera is the edge, right? Often there's a gateway that's the edge. The camera can be a normal camera.
Right.
But the processing can happen in some small computing devices attached to the camera, or a set of cameras, or a set of sensors. So is that the most common? Because like you said, it's very difficult to expect every camera manufacturer to have a computing attached to it.
No, definitely. So when we talk about edge computing, what we end up having is that there will be a group of sensors attached to a particular processor, and that processor is the one that does a lot of processing for all of the sensors, and then decides on what information needs to be sent, how it needs to be sent, what data protocol or what communication protocol is going to be there. So you'll have some kind of a transceiver as well in most wireless applications. So all of that, the entire system then basically becomes your sensor. Like that, you would call it a sensor, but if you give it to any hardware designer, they would say, okay, this is the processor, this is the sensors, all of the raw
sensors.
So
the sensors can be not just anything from the market.
They can be anything from the market.
Intelligence is edge intelligence added to the hardware attached to it, and it's not in the sensor itself.
It's not in the sensor itself.
It makes it easier to build solutions.
Correct. Yeah. So you would develop an algorithm and port it to a processor, not to the sensor, and only attach the sensor to the processor with the right pins, and then that will be it. You can have some transceiver as well, just to make sure that
so in this environment, when there are heterogeneous, like we take 10,000 cameras, I'm sure the cameras are of all types. If you just take Hyderabad City, they're not single vendors.
Right.
So standards play an important role.
Absolutely.
So what kind of standards help here in managing this large number of devices, large number of types of devices?
So there are a couple of standards that you have to look at. One is basically just from the sensor communication to the processor itself. That has to be standardized. Okay, and then from the processor, how do you communicate to the cloud? That has to be standardized. And there are multiple levels of communication that happens. Like for instance, you can basically standardize the modulation or the frequency at which you're going to send wireless transmission. So that's the most base layer, like the physical layer of communication. But on top of it, you have to standardize things like information model as well, like what the protocol is going to be. So that is one layer of
video. What kind of video streaming standards?
Yes, exactly.
Some of the sensors. What kind of standards?
What that data means. Again, is another layer. So all of those layers of communication need to have their own standards. So I mean, an example that I always give my students is that whenever we are communicating, right? So the voice that is basically emitted by our vocal cords is basically the physical layer, or what is being transmitted in air by transceivers. The language that I'm speaking is the second layer of that communication. You can speak, like you can create sound and I'll be able to hear you. But if I don't know the language you're speaking, it's not going to be any use to me.
Some incoherent.
Yeah, it's going to be incoherent sound. So that is exactly what happens in wireless communication as well. Like there is a chance that, I mean, you have to first figure out what modulation and frequency you are going to work with. So that's your vocal cords. And then on top of that, you have to define the protocol that you're going to use. That will be your language. On top of that, you have to define mannerisms, like when you say hi, should I say hello? So all of those things actually happen, like in wireless communication as well.
And those non-verbal cues are an important part of communication.
The communication will absolutely fail.
Yes, the same words said differently, like with a vigorous nod of the head, or, or a very stern look on the face. Same words can mean very different things.
So that's how actually, and that's true even for wireless communication, like in machine-to-machine communication. There are a lot of actually top-level standards as well, like protocols, like for instance, wireless communication, which feels like very easy for us, like you can just put SSID and password and you're connected to the internet. But a lot of it goes behind, like for instance, your node, which is basically the edge, or your phone in this case, has to tell the router, this is my name, this is my mic ID. The router says, okay, this is my SSID. The phone says, is this, I'm doing for this SSID. The router says, yeah, this is the SSID. The router asks, what is the password? The phone says, this is the password. And then it says, is it okay? And they say, yeah, it's okay. Can I communicate? Yeah, you can communicate. Can you say, give me this? So all of this happens behind the scene. Like there's a lot of back and forth communication before actual communication can take place. So this is all part of the protocol, and you have to write a very standard protocol, like very sort of rigorous, like it has to be a very well written protocol to be able to communicate all of this effectively.
So I mean, like you refer to like say the devices machine to machine. Now here we are talking about like case. I mean, two machines could talk to each other through a central kind of some kind of a solution algorithm running in the cloud. But other use cases where machines talk directly to, I mean, on the edge, two edge devices talking to each other without even involving the central.
Yeah, that actually happens. We call it the mesh network. It depends on what you're trying to do. So one of the problems that one of this teams is trying to solve, or one of the student teams is trying to solve in IIIT, is that can we make a street light that is smart enough to recognize whether movement is happening, and if movement is happening, it should switch itself on. That's the basic thing that everybody else also does. But I think the one thing that they're doing interestingly is that they're trying to figure out if that street light can tell other 4 street lights to switch on.
So the direction of
depending on if you're driving in a particular direction, the car, X number of street lights should be turned on in front of you, so that you feel like, okay, it's a well lit road, right? If the street light that you're directly below or slightly just below, only that switches on, I don't think it's going to be a safe driving experience. So that's what they're taking into account. Now the point is, you can basically take that information, whether of the car being under one street light, and send it to the cloud.
And then that decides the direction.
Says, okay, these 4 street lights should be on. Next 4 street lights. Or you can just tell this street light just to communicate this switch on, switch on, switch on, switch on. And then all of the 4 switch on. When you go forward, this guy basically senses that your presence, and the next one also switches on, and then this one switches off. So that is more like a mesh network. That in which you have to write an algorithm which basically just defines how a particular edge device is going to behave with its other edge devices, like fellow devices.
That's aware of.
Yeah.
Now, like the drone swarms is another example, right?
Yeah, exactly.
The drone swarms have to do this.
Right.
When you have like some tens or hundreds of drones that are collectively doing some tasks.
Right.
It's not possible for them to all 100 or so to communicate and then coordinate through a server.
Right.
So it must be using some combination of server telling what to do, and also between themselves P2P. Also figuring out what to do.
Definitely, there is peer-to-peer communication because they have to know each other's location in real time. I mean, even if there is a lag of a few milliseconds here or there in communication or processing, there can be calamities. So we have to make sure that there is some real-time or very, very low lag communication that is happening peer-to-peer in these kinds of situations.
I remember this use case from many years back where there were TT balls which had a small low-power transceiver and a payload.
Okay.
It could be an infrared sensor or some other sensor, and these were scattered from a plane onto a jungle or some wilderness. Now they're all low power transmitters. They form a network, and then it quickly forms a route to the edge where you have a main receiver.
Okay.
And now in one shot you map out this. I have a small GPS location as well. You have now mapped out a whole area. They form a network and they transmit. Each one transmit its location and what it's seeing right now. If it's a motion sensor, it's just telling I see motion or not.
Right.
And location. Now suddenly on the edge, and it also communicating. It does two functions. Its own data it's passing, and if it gets data from another sensor nearby, it transmits because the network route got formed. It's a dynamic network. And it was a phenomenal use case.
I mean,
and it's still relevant. This was almost 20 years back.
Yeah, I mean, imagine like if you put very simple sensors on it, temperature, humidity, you will suddenly see an entire temperature map.
You can map out the whole area that you can't access otherwise.
Right. I mean, I think that would be great.
And for it today more practical. This was a defense use case. It was very expensive at that time.
Right.
But I'm sure you can do it for all kinds of stuff now because it's much more affordable. Technology is much cheaper and also lightweight.
Yeah, for things like, for instance, bushfires in Australia, you can basically figure out what the current temperature or humidity of a particular patch is and figure out whether it's vulnerable to fire or any other like disaster management. These kinds of use cases are actually very
very I mean, up close and personal, what you can't get from a drone or a satellite. So it's very, very practical today. Now, obviously these are solutions where like there's intelligence. Like if you talk about the street lights or crowd management, so there's always some algorithm that's running, right? And in today's world, most of these algorithms are not rule based. So all AI, machine learning based. So how does machine learning AI fit into this whole network of cloud and edge?
So this concept of AI is very interesting actually. What I think of AI is basically we are basically doing some statistical mechanics or figuring out a pattern without actually figuring out that pattern or without having actually to do the mathematical rigorous mathematics to figure out that particular pattern. What happens is, for instance, if you take a very simple example of classifying something, like if you take the Cartesian coordinate system, you map out a circle's a function, and you say whether the point is inside or outside the circle. So you will say x square plus y square is less than or equal to something. That is the radius in which it's inside that circle. Very easy to do. You can analytically do it. X square plus y square is the function of the circle. We know that very well. The problem is when data becomes large. For instance, if I give you a voice, a voice file, right, which has either my voice or your voice, right? And if we want to figure out whether this voice is Ramesh's or Aftab's, how do you write a mathematical function for that? So generally, voice is basically voice is represented as amplitude versus time, right? I mean, either it's a .wav file or even if you encode it in MP3 or whatever. At the end of the day, it's amplitude versus time. So you will have to write a very, very complicated looking function probably that will basically map out the amplitudes that I speak and the amplitudes or the way you speak and the frequencies inherent in it and figure out whether it's my voice or your voice, right? So the analytical function that will basically give you this will be tremendously hard to come up with. You can possibly come up with, like, it's a mathematical possibility to come up with it, but
it will be extremely hard and computing intensive
to get there.
Yes.
So that is what we do with AI. Is basically we try to train. At the end of the day, neural networks, I still call them mathematical functions. So we try to train mathematical functions such that we give them a lot of
probabilistic rather than deterministic.
Yeah. So we give them a lot of voices. And we say, okay, this is Aftab, this is Aftab, this is Aftab.
So learn the patterns.
Yeah, so that we can learn the patterns, what are common, and then we can give you some your voice patterns, and then when we give it a new file, it should be able to recognize whether it's yours or mine. So at the end of the day, AI is basically a very, very efficient tool to come up with mathematical patterns or functions that would have been very, very hard to come up with otherwise. So that's the beauty of AI. The problem with AI is one of the other things, nice things about AI is that it's actually very, the processing required to do AI is not a lot. A lot of people believe that it is, but the processing required to train it is a lot. Right?
So you're processing large amounts of images or voice samples.
Exactly. So somewhere, some server needs to have 1,000 voice files for Aftab and 1,000 voice files for Ramesh, and then process it, come up with a net. The good thing is once that neural net has been made or some kind of algorithm has been set up,
very light.
Then it's light enough. Then you can basically port it to another processor and then give it a new file. It should be able to determine it quickly enough. So even in terms of computing cost, it's not a lot. So that's actually one of the nice things that that we can basically do with AI. It's cost effective as well as time effective as well as not very compute intense.
And then like now, so what's the edge angle? I mean, like supposing we already discussed saying like, okay, we are crossing image or even sound. You're recognizing something in the sound. It could be a person or anything else. So the sound is still relatively lighter data, but image is very, very heavy in terms of quantum amount of data. So what is the edge angle when AI is in the picture? I mean, like, can we do anything and everything on the edge, or would there be constraints?
So one of the problems with AI is, like we said, it's deterministic. It's probabilistic. It's not deterministic. So what will end up happening is you might get false positives or false negatives depending on what your algorithm is or how much your training data is there. So having a very, very large amount of data to be able to train the neural net is a biggest problem that AI.
But that will be done on the server sometime because it's a one-time.
That you can do on the server, but just having that data annotated properly or knowing knowing what is what in that data, that itself takes a lot of effort from both humans as well as computers. Right, and then once that is done, then you can basically put that information there.
And can you optimize a model, a lightweight model that can now go run on the edge?
Right.
If you have to detect a face on the edge.
Right.
So the model should be on the edge.
Right.
So now what kind of, to do such a thing, like if you're going to do image recognition or a face or a speaker recognition on the edge, what kind of typical computing is required on the edge?
So see, if you look at all the variants that we have these days, I mean the microcontrollers and the processors that we have, we literally have hundreds of them, right? Going all the way from very, very simple 8-bit processors, controllers, all the way up to 64-bit.
Raspberry Pi. And
Raspberry Pi
through to
that
some
entire
robust
more industry grade ones, and all the way up to like Jetson boards and everything from NVIDIA that are actually like they basically come with fans and everything else for providing cooling. So this entire spectrum of devices are there. So at the end of the day, what you have to figure out is how much power you want to invest at the edge. Like for instance, the moment battery operated things come into picture, right? I mean, if you want to do something that is remote sensing, or like you said, the example of ping pong balls, right? The biggest problem with that is they're not grid connected. So then the moment you do that, a lot of processors basically go out the window. Then you have to worry about every ounce of power that you're consuming, why you're consuming it, where it's going, and all of those constraints then become the biggest problem, right? The other thing is in terms of space, the requirement, like how big the form factor should be, can be one of the constraints. The third constraint would be what communication you're using. So, for instance, some processors these days come with inbuilt transceivers for Wi-Fi, for BLE, for LoRaWAN, all of those things. So, which communication protocol you want to use might determine what SoC you're using. So, all of those constraints are there. So, the choice at first might look infinite, that there are so many processors to work with. The moment you start adding these constraints, you will figure out that there are not a few. There are not many there, and at the end you will have the actual algorithm that needs to be run, right? So after all of these constraints that are there, you will figure out that five processors are there now. Now out of those 5 processors, pick the one that actually can deliver you the processing power that is needed for your AI.
Now, when something like Jetson you refer to, if somebody says like this is AI ready board for the edge, what are they talking about? Why is it AI ready? What in it is making it AI? It's obviously not a GPU, right? It's not that you can do some huge computing on the edge. So when they say AI ready, what are the typical attributes?
So I want to be clear about this fact that when I said AI is actually light at the edge, I was comparing it to the kind of algorithms that you would run on the cloud or the training that you would have to go through. That is very, very compute intense. But AI itself is fairly compute intense. If you look at what the alternative it is, don't do anything, just take the data and send it. That is basically the least computing.
Yes. So for this use case, you need the computing unit. Yes.
Right. So this is the least computing that you can have. When they say it's AI ready, what they're trying to say is that it can basically handle a lot of data throughput and some AI algorithms that are compute intense just because of the fact that the data is too much. For them, it's still appropriate. I mean, it will be able to handle that data throughput, right? So one of the first problems that I actually faced when I started in industry 10 years ago was at back in the day, this self-driving cars hadn't come, right? I mean, people were still talking about it. So I was in analog devices. Our task was to come up with a processor that was able to generate or was able to basically process very large amount of throughput that would come from a camera. So you would have like these cars like BMW and all the say, Tesla for today. They will have a camera, and the camera feed that is coming in needs to be processed. Simple things need to be processed out of it. Things like, can you recognize that speed, the speed limit sign, right? Now the problem is, if you basically you can't have very blurry cameras because they have to be high definition. Because again, I mean, there could be fog, some obstruction could be there, or anything of that nature. So you can't have very blurry cameras. They have to be very clear, and the signs are also not that clear. Sometimes they're rusty or whatnot. So you have to have decent HD cameras, like decent definition cameras. Then you can't have very bad FPS also. The frame rates can't be bad because sometimes you're zooming past the speed limit sign.
In a split second, you have to
in a split second, you'll basically get away from the sign and you would not even catch it if the frame rate is very low. So both high definition has to be there and high frame rate has to be there. These two combine to give you a very high throughput. Like, how do you process this data very fast? So the way analog devices were solving it, they were basically making a specific processor that had a lot of silicon area, like the core, specifically for a digital video processing core.
Okay, so the video processor was built into the
processor itself. That's all we needed was the video feed that is coming in. You write your algorithm, whatever you want to process on that is your problem. But the digital video processing core was specifically designed to handle very large throughputs of data. So that was like in terms of like, and it was basically taking up quite a bit of area of the silicon floor, like the actual processor size. Something like 50 or 60% of it was just the digital processing core. So you can have these kinds of innovations inbuilt. Like that's what I would call camera ready processor now. So an AI ready processor, if you're calling Jetson board that, they probably
some libraries are built in already. What you need,
not just the libraries, even the hardwire, like the way they have actually made the code itself, could actually have some hardware or some silicon floor specifically dedicated to AI computing or edge computing or something like that, so that everything becomes easier that way.
Or even like the startup that is there in IIIT, Manjira Digital System. So they have accelerators.
Right.
And they are claiming also like edge is one of the use cases.
Right.
You can write custom, you don't do custom hardware. You do custom accelerators.
Right.
And so it's better than just doing it on a normal processor.
Right.
So you put their chips along with your main CPU. You have custom accelerators that are meant for like images or sound or whatever it is that they're meant to do. So now there's also, I mean, like references to creating custom, of course, expensive, by using, like say, FPGA, for instance. What is that FPGA's role in edge computing? What can it play?
So I think it's great for testing out things,
but not for production.
Yeah, but not for production. Yeah, at the end of the day, if you're doing anything of the north of 1,000, 10,000 pieces, you would definitely want a silicon floor properly designed and commissioned, and production to be done.
So concept in FPGA, and once you have it done, then you actually go and get the chips done.
So for us, like in IIIT or like academic institutions, research institutions, it's always nice to have these kinds of
because you're doing in very small volume, so you need something like this.
Exactly, to test out all of your algorithms, to figure out what needs to be optimized and everything else. But at any scale, if you're doing anything, it'll be better off if you go with the tape out the silicon.
So I know work that's happening in IIIT and elsewhere, both in terms of trying to optimize the algorithms for the edge and also optimize the edge hardware for the algorithms. Right. So what's your take on it? I mean, like, what's happening in that space?
No, yeah, I mean, this is the same example that I gave with the video processing. That is basically optimizing the hardware for the image processing, right? So again, if you optimize your hardware for AI processing, you would probably have an AI core, and again, some of these new processors have those inbuilt AI features in them. So that is your customizing your hardware, right? As far as customizing software is there, I think that's a very old trade. I mean, people always customize software for hardware.
Yes.
Right. I mean,
the performance excess.
Exactly. It depends on how many cores you have. Can you multitask? Can you multi-thread? Can you, for instance, if you are worried about power too much, can you go to sleep very quickly? Like after doing some tasks, go to sleep so that power consumption is low. So all of those things are us trying to optimize our software so that our hardware like can actually handle that all of those constraints of power and transmission and everything else.
So a few comments, questions. So good processing power on a small hardware. So that's happening, right? I mean, we are getting enough small microcontrollers that you were referring to some time back.
Right.
That's now got good power. I mean, I was surprised when I first heard that, like on a simple, not even Raspberry Pi, even on an Arduino board, you could do image processing algorithms.
Yeah. I mean, so I think we are definitely getting a lot of hardware. Like we have actually like some of the hardware that I'm familiar with, like some of the chips are something like 5 millimeter by 5 millimeter in size, right? So it's almost like a grain of sand, and you can still do a decent amount of processing. Like they are 16-bit, 32-bit processors that are that small, sub 1 centimeter by 1 centimeter size, and you can still get a 32-bit proper Linux kernel installed on it. Do Python coding, you can do like a couple of gigahertz of processing as well on that.
That's wild. Such a small
unbelievable
processor.
Yeah. So because of that, what's happening is definitely this helps devices on the edge. When I said in some time back, I said one of the constraints can be through your footprint, right? The how much area your device takes at the edge. If you have these kinds of very, very small processor, it's always helpful because you can.
And you're talking about ingestible sensors now, right?
Yeah,
that you just swallow, and those have to be this small.
Exactly. So because of the power that these processors are now carrying, you can basically start doing that as well.
But that's interesting. So there is a comment on V2X.
What did you say? Transfer speed bottleneck. Yeah. How would 5G affect it? Yeah. So this is one of the things that people have been talking about as well. How you would want to integrate 5G into this solution, and people have been advertising 5G a lot for IoT applications, that we can probably connect everything to the cloud with 5G. It'll definitely give you a lot of bandwidth in terms of data transmission, but it depends on what the eventual hardware for 5G is going to be, right? I mean, you have to basically so you have solved one problem.
It's also become very inexpensive.
It has to become both inexpensive, low power, as well as low footprint. I mean, it has to be, if it's a very large antenna and SIM card has to be there and has to be registered and everything,
it defeats the purpose.
Basically, you can't have 10 billion of them, right? You can't put it on every chair and every door and every object that you have. So at the end of the day, it all boils down to the cost of it, the footprint of it, and the hardware specifications that we get.
So they're working on it, for it to be used in such solutions, it has to be IP that gets embedded on any chip.
Right.
So is that the direction that it's going, 5G? Like you get like 5G IP that's very small can just get burnt onto the.
I'm not sure actually whether work is going on in that direction, but I think it definitely should.
It'll eventually head there.
It
will eventually head there. So the V2X for light turn on roads. What is V2X? I haven't come across V2X.
Yeah, I don't know. It's probably some protocol.
It's a vehicle to. I think it's there's a vehicle to vehicle communication.
Right.
So there's probably vehicle to anything. So
it's part of those new edge protocols that are basically coming up for machine to machine communication.
So which needs that
They're popping up by the dozens every day.
Actually. But what are the good mesh? I mean, such solutions where like you're having local communication. What are the protocols coming up? Because everything that you see, standards that you see, is all from the sensor to a central, right? With whatever you including 5G. What are any standards or any protocols coming up for where it's on the edge itself directly mesh? You refer to mesh, machine to machine or device to device. Are there any standards coming up? How would they communicate if they have to communicate today?
The problem with that is, I mean, because a lot of standards are coming up and people are trying to solve specific use cases, coming up with a particular standard. What ends up happening is that you have too many standards, right? So at the end of the day, then basically you have to you can probably do vehicle-to-vehicle communication with a particular standard, or street light to street light communication with a particular standard. But if you want your entire city to function seamlessly,
open standards,
then you have to have some standard that everybody is following and everybody is basically and it's open, right? So that is one of the problems that that these new age standards have. So we have to then figure out like it's like natural selection. Depending on what all constraints and advantages these standards have, hopefully in time one of them will survive, and we'll all end up using those standards. Like for instance, Wi-Fi has beaten so many other standards that came up in that generation. So everything else will probably hopefully die down, and we'll have one or two standards.
Even Wi-Fi often, I mean, like as a P2P. I mean, today, like when you have a Alexa or a Google Home and you're playing music, or you're using Fire Stick, or you're doing a Chromecast. No, these are all using Wi-Fi on the edge. Right? You're not connected to any server. The devices are talking to each other using Wi-Fi.
Yeah.
It's not very common.
They're talking to Alexa, and then Alexa is talking to the server.
In some like
Google Nest or whatever
if you're doing a Chromecast on your phone.
Yeah, that is right. Yeah, that is
your phone is directly talking to the TV.
Right.
And so Wi-Fi was today. You don't think of Wi-Fi that way, right? You look at Wi-Fi saying, "Look, that's my access to the network."
Right.
You're still looking at it as a network infrastructure to connect to other servers and such, but you're not looking at as devices on the edge could do it.
Yeah, I think let's stick to that. I mean, we shouldn't look at it from a perspective of edge-to-edge communication or peer-to-peer communication, because Wi-Fi wasn't optimized for that. Wi-Fi was optimized for something
only to be a router.
Exactly.
To go to some mothership somewhere else.
Exactly. I mean, and plus the way Wi-Fi has been written is basically to provide a lot of bandwidth for things like, and the generations that are coming up with very, very high video streaming, or if you're playing some games or anything like that. So a lot of data throughput can be put on Wi-Fi. The moment you do that on a particular protocol, you're basically compromising on other things. Your power consumption that will happen if you have a Wi-Fi communication will basically be higher if your data throughput is higher.
They're not ideally.
So they're not ideally suited for. So they're suited for something else. They're invented for something else.
Are there other standards coming up for this vehicle to vehicle, machine to machine?
So yeah, I mean, for instance, there is LoRaWAN that is being talked about a lot these days for low power communication. One of the reasons why is because of the fact that it's again invented for IoT applications. Like so, it's
but does that standard factor in machine to machine?
Yeah, it is peer-to-peer as well. You can have peer-to-peer LoRa communication as well, because the LoRaWAN, like the protocol that is written on top of LoRa PHY, that is a star protocol. But you can, if you just follow LoRa this thing like modulation, you can basically come up with your own radios as well. Just peer-to-peer.
So two LoRa's.
Exactly.
Whatever the transceivers can talk to each other.
Exactly.
So one temperature sensor can talk to another temperature sensor.
Exactly. Yeah.
And it's designed to be low power.
Yeah.
So it's probably it's good. So even if you take things like say 5G, I'm not sure. I don't know much about 5G nuances, but technically, if my mobile can talk to a tower that is like several kilometers away, right? I should be able to talk to another mobile.
Correct.
Technically.
Yeah.
Right. I can talk to this tower. Tower can talk to me. Yes, tower has more sophisticated infrastructure for network routing and other things. But from a communication protocol standpoint, it can technically communicate to another device, but it's not. I don't know if it's designed to do that.
No, it's not designed to do that. I mean, yeah, because then you have to worry about things like network congestion and everything else. Like things like what ends up happening is if you're the only two people in the country or in the world, then it's okay. Then you can do whatever you want. But if there are multiple people trying to talk to multiple phones, probably at the same time, then it becomes an issue of how you are going
to. Your phone will become like a mini tower now.
Exactly.
So
and then the sophistication that you are saying in a tower actually comes because of that. I mean, you have to basically slice your bandwidth that you're getting into frequency channels to make sure that multiple users can use it. And then even that is definitely not sufficient given the number of users that we have. So you slice it in frequency, then you slice it in time as well, so that you give a slice of time frequency block
so which would not
to a particular user. It will be
so without replicating a tower in the phone, two phones cannot communicate.
Yeah, exactly.
The standard is not even meant
if they're the only two phones in the world, probably they can. But if you want to make some kind of a mesh, it's going to be hard.
It's not an ideal standard.
Right.
So Laura, are there other standards that are coming up for this?
Yeah, I mean, I've heard of NB-IoT is there, which is again specifically designed for IoT applications. So Sigfox is there, 6LoWPAN is there. Many again. There are no dearth of standards.
So when standards like 5G, when 5G says like it is suited for IoT, they are talking about sensors talking to a central server only.
Right.
They're not looking at an edge to edge. It's not in their purview.
As far as I
haven't come across. It doesn't seem like
it also is a startup.
They're assuming there's an infinite communication bandwidth and infinite computing bandwidth available there.
Yes, exactly.
So you need to talk to each other. You talk through the server.
Right.
So somebody else commented saying we have good processing capabilities on the edge, but our interface to the edge computer might be slow. But that's not the case right now, right? The communications is quite, in fact, that's more than what an edge needs.
But the interface to the edge computer might be slow. I'm not sure what interface to the server. Sensor. Okay. Yeah. So that is also one of the problems that we have. So when we were talking about standards and protocols, I told you that there are standards that basically help you communicate with the sensor to the processor or to the edge, and then from the edge to the some gateway that you're talking about. So all of the standards that we talked about, like NB-IoT, LoRaWAN, all of those, Wi-Fi even, they are all basically trying to communicate from the processor or the transceiver to a centralized gateway. If you want to just locally do some very quick processing from the sensor or transmission from the sensor to the processor itself, we have a lot of wired protocols as well. I mean, again, I don't want to go into the nitty-gritties of it, but there is UART, there is SPI communication, there is I2C communication. They're all basically wired communication that make sure that data is basically sent to the processor in a sort of a friendly or recognizable manner. So yeah, that can itself be slow sometimes. I mean, again, depending on, for instance, if you have a camera that is basically taking some images, you have to make sure that the communication protocol from the camera to the processor itself should be able to take that data throughput. Only then the processor will be able to process that data throughput, right, properly. So that processing itself, that transmission itself sometimes can be slow. So it's
a long ways to go, right? I mean, I read somewhere like in a typical car, even a medium, not even a high-end car, there are hundreds of kilometers of cable running inside. That much of sensors and actuators to be controlled.
Right.
And they're obviously running using cables. One, it's probably cheaper, but also more importantly, I don't think there are good communication channels that can handle, like say, hundreds or thousands of such sensors and actuators in a car.
Yeah,
it's not like you still need power cables, but that is easier to run through the car. But a lot of it is control cables.
Yeah, I mean, the moment you throw anything in the air, it's easily catchable by other people that you don't want to be involved. So if you basically have a wireless sensor from your car's back end to your front end, it will basically transmit everywhere, and 5 other people can catch it, and if they're able to decrypt it, I don't know.
And they can probably control your car.
It can have consequences. Even if it doesn't have consequences, one of the other things that people worry about a lot in the automobile world is reliability. And while we have very good reliability with wireless protocols, it still can't beat wired.
Not enough for a car.
It's not enough for a car.
Vehicle and people.
Exactly. I mean, the planes, for instance, I mean, you've probably heard this. There are 3 or 4 processors that are basically doing the exact same thing. So that if one of them burns, there are still a couple of more to handle the same.
Level of redundancy you need.
That is the level of redundancy they need for safety.
So at some level, I mean, at one side, it looks like we have come quite far along.
Yeah.
On the other side, if you can't create a wireless network where the
if
sensors in the car can communicate with each other reliably,
right,
way far behind. So on that note, I would like to thank Aftab. Thank you, Aftab,
Thank you so much,
for joining us.
Here.
And so this is Ramesh Loganathan signing off until next week. Thank you.